So far this week, we've talked a lot about steak, but elasticity is a concept that occurs in many different foods. And soon you're going to see an excellent example of this when Bisss Yosses cooked strudel for us. So strudel has a lot in common with other bread doughs, and we're going to talk more about this later on in the course when we talk about baking in general. But for the purposes of this segment, I'm going to tell you a little bit about gluten. And gluten is the protein that gives strudel dough its very, very special characteristics.
So I'd like to do a very interesting recipe that is a very old-fashioned one, and it's strudel dough. So it's a recipe from Eastern Europe, and it only has 4 elements. So it's salt, flour, high gluten or bread flour, some kind of salad oil, and water. So those 4 elements, but it makes a really an amazing dough based on a technique that we're going to use here. And that technique is to really overwork the gluten in the recipe.
So gluten is a component of flour, and it's a protein. And the protein content is usually about 10% in flour, although it's going to depend on where you buy your flour, actually. It's going to depend on where in the world you buy your flour, but also where in the US you buy your flour, but usually around 10% or so. The rest of flour is about 70 to 80% starch or carbohydrate.
What happens is that the gluten, and there's more gluten in high gluten flour, obviously, bread flour, because that gluten is necessary for the bread to develop its large structure through fermentation. So the air pockets of carbon dioxide are produced by the yeasts, and then that expands the bread. But if there's not enough gluten in it, the bread cannot rise. So we try to, in this case, we use that gluten to make a very elastic dough. So these strands become longer and longer and stronger and stronger.
The special property of gluten in molecules is that some of the amino acids are cysteine molecules. And cysteine amino acids have a sulfur bond on them. And this sulfur can form a very, very strong bond with other sulfurs on other cysteines in other glutenins. And so what ends up happening and what's causing the gluten network to form is that these cysteine molecules bind together with other glutenin molecules, and they cause this very intricate network, a very, very large network of glutenin molecules, and this is the gluten network.
So I have the flour in this mixer now, and we'll just start to mix that around. The first thing that we add is the oil, 2 tablespoons of salad oil. It's 12 ounces of flour and 1 cup of water. As it starts to form, you already see that there are these strands. You already see there's these sort of strings forming. Well, that's the gluten, but it hasn't come all together yet. So we'll just run it slowly as you see this, the water go in. And then something very interesting happens. It forms a ball, but when you add the salt, it becomes even more elastic.
So as I mentioned, there are a few of the amino acids along these molecules that are charged. And as you add salt, you know that salt is positive sodium ions and negative chloride ions. And so these charges are going to be attracted by the charged amino acid. So the positive sodium ion is going to go to a negatively charged amino acid. And so this means that the charged amino acids on the glutenin molecules are going to be neutralized. And so as the glutenin molecules stack up, as you knead the dough, they're going to be able to come much closer to each other because there are not the charged amino acids that make them repel each other. And so the glutenin molecules will get closer, and as you then knead the dough, they will be able to glide each other and then form slightly stronger hydrophobic interactions that hold them together and make it possible to stretch the dough.
So the whole nature of the dough changes. Okay, so the dough has come together here into a fairly tight ball, and we'll add the salt to complete the process. Now, in most recipes, the last thing we want to do is develop the gluten. What we want is for doughs to be soft, so that when they bake, they sort of crumble inside your mouth. You have this very kind of luscious, soft texture, or flaky, as we would normally say in baking. So flaky pie crust, flaky croissant, all those things are a direct result of manipulating the gluten. In this case, we over-manipulate it so that it becomes very elastic. And what we're going to do is then we're going to allow this gluten to become very elastic, and then we let it rest for a couple of hours in a cold environment in the refrigerator. So this is going to go on like this for about 8 minutes. So it's formed into this very tight ball, and it's been running now for about 8 minutes. So we'll take it out. And also it has heated up, so you will notice that it becomes warm from all that friction. But what we want to do is we want to allow the flour to absorb all that water. To fully absorb it takes 24 hours. And we'll refrigerate it and we'll come back and visit it later.
And absorbing water helps develop the gluten network. You can imagine that if all the gluten molecules are not dissolved in water, they will not as easily be able to stretch out and form bonds with each other. The other thing that happens is that the starch granules, when sitting around in water, are going to swell. And as you remember, gluten is only less than 10% of the flour. And so the dough is going to have a quite small proportion of gluten. It is what's giving it the structure, but the actual sort of mass of the dough is the starch. And as it swells and develops, this is what's giving the dough its final consistency that you can then make the strudel with. As we start to knead the dough, we're slowly unfolding the glutenin molecules, and we're unfolding the network, and we're aligning them. And they are going to be aligned so that there are hydrophobic interactions, van der Waals interactions, that are binding them together. Now, what happens as we're kneading and as we're stretching the dough is that these bonds, they're weak. They're strong enough to hold the molecules together, but as we knead the dough, they start to slide the molecules along each other, sort of like this. And this is what's giving the elastic property of the gluten network. And so as we work the dough, we get more and more of these aligned molecules, and this is then making the dough more and more elastic.
So you're trying to let those gluten strands relax. And as it warms up, as you work with it, they will also have the ability to stretch longer. So maybe, Tracy, you could take your... Okay, yeah, we can start to take from the center now.
So Bill started out with a small clump of dough, and then he stretched it so that it became very, very thin. And here's a microscope image showing the dough stretched so thinly that you can actually see the fibrous structure of the gluten network somewhat. And you can also see that the dough is stretched so thin that you can almost look through it. That's how thin you can stretch it while still holding it together. And this is thanks to the gluten network.
Okay, so now our filling. So these are sautéed apples, breadcrumbs, golden raisins that have been plumped in hot water. Now, the thing you don't want is you don't want these edges anymore. We use them just to be able to stretch out the dough, but since they're so heavy, they're no longer of any use to us. As we roll it, to help the layers stay separate, we'll put a little sugar in there. Okay, and this is the reason we use these towels, because at this point, we want to try to get nice, smooth of a cylinder as you can.